And today we're going to take a look at symmetry and coordinate graphs. You dealt with this back in geometry also when you were doing your transformations, things like reflections and rotations, point symmetry and line symmetry. And it's really not that much different now. We're just looking at it as it pertains to graphs of functions and such. So symmetry really is just about when one shape becomes exactly like another when you flip it, turn it, or slide it. So just like really you were doing in geometry with your transformations. And we've got a few different types of symmetries we're going to talk about. First one's going to be symmetry about the x-axis. And really all this is a reflection over the x-axis. Just like you saw in your geometry course. It literally flips over the x-axis and the shape, size, and shape is preserved. Symmetry about the y-axis is exactly the same. So reflection across or over the y-axis. Next type we're going to take a look is when it's symmetric about the origin. And when it's symmetric about the origin, this is a type of point symmetry. And you can think of these most easily as a 180-degree rotation. So, quick example, we'll take a look at more here shortly. If I had some figure, let's just say some triangle here. If I took this triangle and this was symmetric about the origin and I rotated it about the origin, this would simply just kind of, let me just draw another one. So let's say that's exactly the same. Not too bad. And this is actually going to come down here, but it would be shifted around like that. And that would be symmetrical about the origin. And there's a little bit more of a technical definition to it, but literally it is a 180-degree rotation about the origin. And if you recall some of your rules in geometry, the xy coordinate, we'll talk about this more here in a second again, becomes a negative x, negative y for every point on that figure. And the same holds true when we're talking about graphs of functions or others. So let's take a look at some simple descriptions of symmetry. So we view the graph here. It appears to have a line of symmetry right down here at the y-axis, such that this half lies exactly on top of the other half. So this is symmetric about the y-axis. Doesn't appear to be so on the x-axis, otherwise this would follow kind of this. That there would be symmetric about x, and if it were symmetric about y, I'd be able to turn it 180 degrees, or excuse me, about the origin rather. And if you want to see what that looks like, you can also kind of just experiment. I took this figure, rotated it, say 180 degrees. Clearly it does not lay on top of itself, so that is not symmetrical. And there it is back to the original. I can check this one here as well. It does not appear to be symmetric about the y-axis, where I would see the same shape reflected across y. If it were symmetric about the origin, again 180 degrees, I would have the same figure, which I do not. But it does appear to certainly be reflected across the x-axis, so this has symmetry across the x-axis. Look at a couple more. Now this one doesn't appear to have symmetry across y, otherwise I should see this same shape reflected over here. doesn't appear to have symmetry across x, otherwise I should see this as well. Actually be the same picture there. But it does appear as though it does have symmetry about the origin, 180-degree rotation, and I see it falls onto itself. So this has symmetry about the origin. Okay, let's take a look at this one. If I were testing for symmetry about the origin, remember 180-degree rotation is an easy check. It does not. If I was looking about the y-axis, this would have to all be reflected over. So it looks something like that. Went a little wide there, that's okay. And if it was reflected across x, same thing, it would have to come down like that. So it doesn't appear to have any type of symmetry across the x-axis, y-axis, about the origin. So just because the figure has symmetry, which this does, I could draw a line of symmetry, it appears as x equals 2, doesn't mean it has the type of symmetry that we're looking for. And so another example here, given the ordered pair, -2, 3, so I'll go ahead and plot that real quick. If I were going to find point symmetric to the x-axis, y-axis, and the origin, pretty easy. This is -2, 3. I'm just going to go ahead and reflect this over the y-axis. So that would fall right here. So that is 2, 3. So the only thing that changed there was the value of the x-coordinate. It just flipped signs. If I reflect it over the x-axis, this is going to go down to -2, -3. So the x-axis is -2, -3. The only thing that changed there was the sign of y. And if I rotate it 90 degrees about the origin, this comes halfway around. It's going to be somewhere right down in here. And actually, as we showed up above, your x and y, the signs will just flip. So I change the sign of x and y when I rotate 180 degrees, so that is 2, -3. And there are my points that ultimately have been reflected across x and y and rotated 180 degrees about the origin. So all those same concepts in geometry are coming up again. So how do we test for symmetry? Well, if I want to test for symmetry, or to see if it's symmetric to the x-axis, these rules pretty much follow. I'm going to see that the geometric rule for, I put transformations here, sorry, this should be reflections. And those hold true. If when you reflect over the x-axis, the coordinate xy also has a pairing of x negative y, so again, what's really changed here is the sign of y, then it has symmetry. And the test that I can simply plug that, the x negative y, so you can flip the sign of y, plug it back into the equation, and if it still checks, if you're still producing the same result, then that is symmetric about the x-axis. And we'll look through some examples here shortly. It's the same thing for symmetry to the y-axis. You have your coordinate and the sign of x flips. So in geometry, we probably wrote these rules more like this. If I reflect across x, my xy becomes x negative y. When I reflect across y, my coordinate xy becomes negative xy. And when I reflect across rotate about the origin, your transformation rule, xy, becomes negative x, negative y. So it's those exact same rules that you learned in geometry in your transformations unit, but now we're using them as they pertain to graphs. And so we'll use those same rules here to test to determine if we have symmetry. So we're going to look about the x-axis, y-axis, or the origin. I'm going to write them down here real quick just so I don't forget. So I have the x-axis, that checks xy, becomes x negative y. I have the y-axis, and xy would become negative xy. and the origin, where xy becomes, and really it's a double transformation over y and then over x, or vice versa, negative x, negative y. So here's how we'll test those. So I'm going to take this, y equals the absolute value of x. I want to check for the x-axis. So any values I plug in here, y equals the absolute value of x. So that's always going to be a positive value. So if I want to check to see if this has symmetry about the x-axis, I'm going to go ahead and plug this in, x, negative y. So if that is, then I should produce the same result. And sometimes this is easiest done with values. But to check here, I'm going to plug in my negative y equals the absolute value of x. So is this statement equivalent to this statement? Well, if I plug in any value for x, let's take 3. And what do I get for y? I get 3. If I plug in 3 here for x, I get negative 3. So that doesn't check. So the absolute value of x equals negative y does not check for the x-axis. So I'll just put a slash through there. If I want to check the y-axis, I do the same thing, but I'm going to put in a negative value for x. So y equals absolute value of x. I'm going to make this a negative. Is that the same thing? And that would be the same thing as y equals the absolute value of x. Doesn't matter what that is, because whatever comes out of there is still going to be a positive absolute value. So this one does indeed check. So it does have symmetry about the y-axis. Let me change that to maybe red here. And last one, let's flip them. So I have a negative y equals negative x. This is testing about the origin. Are these the same? And what happens when you get this, if I plug in a value here, I'm going to actually get the positive value because it is the absolute. And so this one does not check either. So that is no good. Very easy to do in a graph. We'll pull up the calculator here. And I plug in y equals the absolute. That's found under the math key over number 1 of x. We'll graph that. And we see very simply that there is no reflection across the x-axis. That did not check. No rotation 180 degrees, but certainly we do have a reflection across y. So let's look at another. So let's check for the x-axis. So I need a negative y value. So is this still equivalent to negative y equals x cubed plus x? And when we look at this, the sign of y has changed, and no matter what value you put in here, it's still not going to be equivalent, this negative y to the positive y. So this does not check. So it is not symmetric to the x-axis. How about the y-axis? Well, I'm going to plug in a negative x. So I have y equals a negative x cubed plus, and we'll just plug in negative x. So again, what happens here? That negative x cubed, well, ultimately that's just going to be the same as x cubed. It's going to be a negative times a negative times a negative. Pardon me, that's actually a negative x cubed because it will stay negative because of the cubing. If it were squared, it would be the same as a positive x cubed. And then that's going to be a minus x. So we see clearly this is not the equivalent form. So that is no good. And the next one, we have flipping the signs of both. So I have a negative y equals negative x cubed plus negative x. So that's minus y equals, that'd still be a negative x cubed, and that would be a minus x. Now, if I just divided all that by a negative 1, that would all just simplify back to. So that is symmetric. So it is symmetric about the origin. If we pull that up on the calculator here, and I put that in, x cubed plus x, I've already gone ahead and done that, we see it does appear to be symmetric about the origin. If I rotate this 180 degrees, it lays right on top of itself. So that's what we're looking to show. Let's look at a couple more examples. So to check the x-axis, I'm going to go ahead and plug in a negative y. So I'm checking to see, is this equivalent to this? And that is not. So it is not symmetric about the x-axis. And we'll check the y-axis. So I'm going to plug in the negative x. So that breaks down to y equals 1 over negative x. Again, is that equivalent? It is not, so it's not symmetric about that. And we'll go ahead and flip the signs of both. So I have a negative y. This is about the origin. And I get a negative y equals 1 over negative x. And we do the same thing. I can divide all this by a negative 1. That'll flip the sign right back to y equals 1 over x, which is the equivalent. So it does check. Let's view that in the calculator. Again, very easy to view visually in a calculator. So I'm going to put this in the stacked fraction. Alpha y equals 1 over x. Graph it. And we see this does indeed have symmetry about the origin. Half a turn, and it lays right back on top of itself. So this one, we'll go ahead and plug in over the y-axis. Let's make x a negative. Parentheses are oftentimes helpful. So I'll simplify this. 2 times negative x squared. Well, that x is going to get squared, which is going to change it back to a positive. But this will still be a negative x. That does not mesh with this, so that is a no. This time we'll just write no over here. If I check about the x-axis, I'm going to make this a negative y. Clearly that's not equivalent. And we'll flip them both. We'll simplify. The negative, again, it's going to get squared, so that's equivalent to 2 times x squared minus x. So again, you'll see this one's not quite the same, because if I were to divide this all by a negative 1 to flip my signs, I actually end up, this will be back positive, equals, but this will be a negative back here. And this, because of that minus right there, is not equivalent. So this is also a no. So this one has no symmetry. And again, we'll verify that in a graph. So 2x squared plus x. And we see what's happened because of this is actually shifted over slightly to the left. And so that is no longer symmetric about the y-axis. Otherwise, traditionally a quadratic would be. So that one has no symmetry. And we verify that algebraically. Even and odd functions, pretty simple concept. It basically all just breaks down to an even function, and you can think of this as the most basic, which would be an x squared. That's your parent quadratic, which has symmetry. That was not a very good one. A little better. Symmetry about the y-axis. So those would be even functions. If it's symmetric about y, it is considered an even function. Conversely, when we have an odd function, the most basic here would just be your parent linear function, or certainly your cubic function. That wasn't brilliant there either, but hopefully you get the point. A little better. So this would be like y equals x. That would be to the first, or y equals x cubed. These are both odd functions, and they are symmetric about the origin. You can spin them 180 degrees. They will lay right on top of themselves. So that's considered an odd function. So when we're verifying graphs, is it even or odd? Well, I'll have to do two things. Is it even? So it's symmetric about the y-axis. Or is it odd about the origin? If it's neither, then we consider that neither. This one I can clearly see is an even function. This one appears to be symmetric about the origin. So this would be an odd. And this one is neither. Okay, let's take a look at just a couple more examples. And we'll do the same concept here. So again, it's just what we were doing, but now we're trying to determine whether or not they're even or odd. And even means that they're symmetric about the y-axis. Odd means about the origin. So again, I'm looking for changes negative x, negative y. And here I'm looking for a negative x, y. So I'll check those. So f of x equals x squared plus 2. So again, this is just function notation. It can easily just be supplemented with the variable y. So y equals x squared plus 2. I'm going to check it to see if it's an even function first. So I'm going to make the x value a negative. So y equals, and we'll just plug in a negative x. That is squared plus 2. Simplifies, y equals, when I square this negative, it's going to change back to a positive. So indeed, this is symmetric about the y-axis, or a even function. Now, is it odd also? They could be, so let's go ahead and check it. Doesn't hurt to practice anyway. So I'm going to make both values negative. So I got negative y equals negative x plus 2. Negative y equals x squared plus 2. Clearly we see with the negative y out here, it is not an odd function. But it is indeed an even function. And we'll graph all three of these right at the end. We'll do the same thing here. I'm going to change this to y equals x cubed plus 3. I'm going to change this to y equals negative x cubed plus 3. Now when I cube, it's negative times a negative, which would be a positive, then times a negative, so this would still be a negative x cubed. And I see that this is not the equivalent function, so this is not an even. So let's check it to see if it is an odd. And if I go ahead and change all this by a negative 1, that gets me y equals, flip it back, minus 3. So again, this is not equivalent. Circle these so we can see. This would be a no. This would be a no. Because of the minus 3, it should be a plus, so this one is neither. And we'll do the final one here. I'm going to go ahead and sub in the negative x. And then simplify. This negative x cubed, as we've seen, is still a negative x. This is going to become back a positive. And we'll see that this is not equivalent. This would be, get rid of this, negative 4x. So this would be the negative 4x cubed plus a 2. If I flip the sign back, it would be a negative y. So this is no good. And we'll flip all the signs. That's a negative y equals a 4 times negative x cubed minus 2 times negative x. So negative y. And this would be then a minus 4x cubed. This would be a plus 2. And if I divided all this by a negative 1 to flip the y back, that would be a plus 4x cubed minus 2. So this one does match up, so this would be a odd. And let's verify all three of these quickly with a graph. And so x squared plus 2. We said this was an even function, so it should be symmetric about the y-axis. And indeed it is. It's our parent quadratic that's just been shifted up 2 units. We'll mention that because we're going to head into transformations here shortly. This one I have x cubed plus 3. So again, this would be our parent cubic function shifted 3 units up. So it's certainly not symmetric about the y-axis, and because it's been shifted, it is not symmetric about the origin. So that one we said neither, and we were correct. And the final one, let's just insert a 4. 4x cubed minus 2x. And indeed we do see that there is no symmetry across y, but it does certainly appear to be symmetric about the origin. And we term that an odd. So that's really all there is about symmetry as it pertains to graphs. So bring any questions with you tomorrow and we'll get a little more practice.